This is section 5.1, day 1, and we're going to talk a little bit today about area. So we're going to kind of go back to geometry, and so we are going to call today fitting it all together. So today's essential question is how can area be approximated when the region is not a geometric shape? So today's focus is about approximation, and fitting it all together is pertinent because we are going to add together different areas. So let's just consider this scenario. We have an object moving at a constant rate of 3 feet per second. If we graph this rate, what does that look like? So if at the beginning they're moving 3 feet per second, and then the next second later they're still moving at this speed, and the next second later they're still moving at this speed, we get a graph that looks like this. So we have this constant rate of 3 feet per second, and that's the velocity. So we also know, so we're going to move for 4 seconds. So we also know that if we want to know about the distance, that mathematically we can just take the rate times the time. So if we think about this, just kind of intuitively, if I want to know how far I traveled in the 4 seconds, and I'm going 3 feet per second, we know that after 4 seconds we've gone 12 feet, right? We've gone 3 feet the first second, 3 feet the next second, and 3 feet next second, and then 3 feet the last second. So we know we've gone 12 feet, a total of 12 feet. So how can we relate this information, traveling for 4 seconds, going 12 feet, how can we relate it to a graph? What physical aspect of the graph represents the number 12? So if we look at this graph, we see that the number 3, the rate of 3 feet per second, is represented by what is located on the vertical axis. And the 4 is represented, the 4 seconds is represented on what is located on the x-axis. So if we look at this mathematically then, 3 times 4 equals 12. So this blue rectangle, the area inside of it, represents the number 12. So we can look at this intuitively and think about an algebraic equation, distance equals 3 times t. Or we can look at this geometrically and say, well, that's nothing more than calculating the area of this region. And that's going to be really helpful if we just focus on turning this into a geometry problem and calculating area. That's gonna serve us really well as we get into more complicated functions, something more complicated than 3, a constant function of 3. So in calculus, I'll talk a little bit about the symbol here, but we're not going to use it too much until the next section. In calculus, we represent area with a special symbol, and that special symbol looks like this. It's an integration symbol, and integration is just the calculus way of saying find the area, or find how much space has accumulated underneath the function. So this blue line is the function 3. Underneath it is this lighter blue region, which happens to be a rectangle. So this symbol means find the area of that rectangle. And so the notation goes like this for this specific problem. We have the accumulation, or the area, from a time starting at 0 to a time ending at 4 seconds. And the area that we're finding is underneath this function here, which is the velocity function. So here's our velocity function, and then this dt is just a dummy variable. This dt is telling you that the 0 and the 4 refer to a time measurement. And so this is the notation we use to represent area or accumulation. And like I said, we're not going to use it too much in this section, but we're just kind of introducing it right now, and we'll use it more as we go throughout this unit. So the area then So this is how we would say this: the integral from 0 to 4 of the velocity with respect to time. And so our velocity function is 3, right? That's my rate, equals 12 feet. So that's kind of how we would say it. Okay, so let's change the problem a little bit. We have an object moving at a constant rate of 3t. So that means that at the beginning, they're moving 0. After a second, they're moving at 3 feet per second. After 2 seconds, they're moving at 6 feet per second. So their velocity is getting faster and faster. So it starts out here, then goes here, then goes here, then goes here. And so that relationship is linear. And so now the concept is the same. The distance that the object traveled is still equal to that area that's under the function. So this area under the function now, under this red line, and when we say under, we technically mean underneath the red line and then trapped between the red line and the horizontal or the time axis. That area is now changing in shape. It's no longer a rectangle, it's a triangle, but it's still geometric. So we can still calculate, we can still use we're going to call this the area method, or the area strategy, to find the physical value of this. So we know that, going back to geometry, area is half base times height. So our base is 4, and our height of our triangle is 12. Okay, so we can do then, if we use our symbol, we're going from a time equals 0 to 4, and we're saying let's integrate, or let's accumulate the area underneath this velocity function here. So that velocity function is 3t, but we're actually going to use this geometry formula here. So we have half 4 times 12. 4 times 12 is 48, divided by 2 is 24 feet. So our distance traveled is 24 feet in that 4-second interval. So the geometry formulas work out really well for linear expressions. You know, the last example was constant, that's a linear expression. This example was a linear expression that was increasing, where they work really well for that. But what happens when we don't have a linear example? A linear expression. For example, here's a velocity. It's 1/8 t squared plus 1. So it has an intercept of 1. There's my intercept. And then after a second, I'm going an eighth foot per second faster. After 2 seconds, if I put 2 in here, that's 4. I'm going a half meter per second faster. So we have this quadratic relationship here. And so if we look at the area underneath that, so trapped between the function here and I go out to 4 seconds again, we can't exactly use, here's that region, we can't represent this region. So from 0 to 4 of this velocity function, 1/8 t squared plus 1. We can't use geometry to calculate this. We don't have a geometry formula for something that has 3 segments and a quadratic top. So using one geometry formula to find the area of this purple region just isn't going to work. So as a result, we need to approximate the area. So we need to develop a strategy here that's going to get us close. It's not going to give us an exact answer, but that's okay. Today's really about approximations. So, what we're going to do is we're going to put a shape underneath the function to fill up that purple space as best we can. And so we're going to try a couple of approaches. We're going to keep this simple. We're going to put rectangles underneath here. And so there's a couple ways that we can accomplish that. Before we do that, let's look at the units. So we still, if we put a rectangle underneath here, we still have units of feet per second times second. And so feet per second times seconds, the seconds cancel, so we will have units of feet. So the units still do work out. Okay, so let's start stacking rectangles. And if we put one rectangle, if we make one rectangle down here at 1 or another rectangle, big long one, up here at 3, that is not going to be too accurate. There's going to be a lot of inaccuracy with that. So what we're going to do is we're going to, for every second we move over, we're going to draw another rectangle. So right now we're going to use these dots. And the rectangle we're going to draw is going to have an upper left-hand corner at these dots. So for instance, when time is equal to 0, my velocity value is 1. So I'm going to draw a rectangle for that first second interval that looks like that. And so you can see that this rectangle is pretty close to the size of the purple area between 0 and 1. So we've got just this tiny little sliver here that we left out. So that's pretty accurate. So we're going to go then, when time equals 1, then our velocity is 1 1/8. So we're going to go with that rectangle and for that 2-second interval. And it's not as accurate as the first rectangle, but that's okay. We're just trying to approximate. And then we'll go out to 2 and we'll recalculate the velocity. Put a 2 in here. It's 4/8. That's a half. So it's 1 1/2. And again, we've got even a bigger sliver of inaccuracy, but that's okay. This is just one approach. And then the last rectangle will look like this. And so we filled this up with rectangles. And the top left corner of the rectangles is what's touching the function. So as a result, we call this a left-handed rectangular approximation. So that's a lot to say. Left-handed, because the left side of the rectangle is touching the function. It's a rectangular approximation because all of these are rectangles. And so we call that a method. And so to shorten this up, we call this an LRAM. And then we put a little number down here. And the number we're going to put here is a 4 because we used 4 rectangles to approximate this, region underneath this function. And so now we're going to find the areas of each one of these things. So that's we call those sub-intervals, each one of these rectangles. And so the approximate area then, I'm going to do the work right on here. 1 times 1 is 1, right? I'm going back to geometry here because I'm just doing areas of rectangles. 1 times 1 1/8 is 1 1/8. 1 times 1 1/2 is 1 1/2. And 1 times 2 1/8 is 2 1/8. So now I can add all of those together and I get a distance of, or a displacement, you can call it either way since this is always increasing, of 5.75 feet. And so that's one approximation. And as you can tell, if you compare the green rectangular approximation to the actual purple area, this approximation underestimates the actual value. But it is one approach. And so we're gonna leave that as one approach. It's an approximation. It's not 100% exact, and that's okay. Note that since we're approximating here, I'm no longer using this notation because this notation is for an exact value. It's not for approximating. So I've replaced this with LRAM4 instead. So that's one method. And so that works out okay. But sometimes the upper left isn't what we want to go for. For instance, maybe we want to use the other corner as our point that touches the function. So what I'm going to do is I'm going to create rectangles now where the right side of the rectangle is now touching the function. So that first rectangle is going to look like this. And so we call this a right-handed rectangular approximation, or an RRAM. And so if we use the right corner of the rectangle, now this rectangle size is a little bit different, but notice this rectangle is now going above the function. And so here's the next rectangle, here's the next rectangle, and here's the last rectangle. And so notice that this rectangular approximation now I'm using this, this first rectangle here is actually the value of the function at 1, so it's actually this value. And so I'm going to do my work right on the picture. So this first rectangle is 1 times 1 1/8, and this next rectangle is 1 times 1 1/2, and 1 times 2 1/8. So those look familiar from the last example. This last rectangle now is going to, we need to have the value at 4. So if I put 4 here, I get 16. 16 divided by 8 is 2, plus 1 is 3. So this last rectangle is 1 times 3. And so if we notice with this approximation, we get a value of 7.75 feet, and this is something that will overestimate. So we can't see the purple area at all. We know it's underneath here connecting these dots. And so this green approximation now overestimates the actual value of the region. And again, it's an approximation. It doesn't have to be exact. And that's okay. So you might be thinking, well, we've got one approximation that's a little bit too big, one that's a little bit too small. What happens if we decide that we want to shoot for the center and get something that is a little more, in the middle towards the average value? So now that means I would have to know these points right in the middle of where I would draw the rectangles. And so what that means, though, and since we're looking for setting up a rectangle that is as tall as what the function is in the middle, we call this a midpoint rectangular approximation. And so, or we call this an MRAM. So this is going to be an MRAM 4. This does require us, though, to find values in between the values that we would see in our table. So if you were doing this on your calculator, you might do a table and set your table step to 0.5 so you can find these values instead of calculating them. So the first rectangle would look like that. 1 is the width, 1.031 is the height, and we get the 1.031 by putting, this point right here is at 1/2, so we'd have to put 1/2 into here and calculate this. And then the next one would be located at 1.5. And we would have to then calculate, put 1.5 in here and calculate this. And I'm going to back this up a little bit. Watch this rectangle being drawn. This is the easiest way to draw it. I start at the center and come out and go down. And then start at this center and then come out and go down. So that's the easiest way to draw it. And then the next rectangle would be at 2.5. And then the last rectangle would be at 3.5. Calculate that value and stick it in there. And so that's effective because if let's take this last rectangle, it's probably the most obvious. We've got a little bit of purple here that we didn't cover, but we've got a little bit of a region here that we kind of let go above the function. So if we could take this and swoop it into here, it would be pretty darn close to an exact value. So the approximate area here, there's the work on the picture. Now we're getting it, when we add that up, we get 6.625. So that's got to be pretty darn close to the actual value. And the actual value is actually, I think, 6 2/3. So 6.6 repeating. So there's 3 different methods: an LRAM, an RRAM, and an MRAM. And so let's kind of compare them then. So this is what you have on in your notes right now. So which one do you think is the closest to the actual value? And you might guess it's the MRAM. It's where we have a little bit above and a little bit below the actual region. So we can kind of fill the gaps with all of these, I'll call them flaps, and we can get pretty darn close. Okay. And that's kind of the justification, is that these flaps can be put into these gapped areas. In this example, there are 4 subintervals. So what happens if we increase the number of subintervals? Let's say we did 8 or 20. And so as we do that, of course, the task becomes much more difficult and much more time consuming. So we don't usually like to increase the subintervals to too high of a number. But as you can see, then we would get a much more accurate picture of what would happen. We would get these gaps that would be far smaller, and same with these over approximations, these flaps, so to speak. So let's take a look at this. This isn't in your notes because this is an animation, but here is the same function, and this one is a left approximation, this one is a middle approximation, and this one is a right approximation. And when I run the animation, these are going to get skinnier, and so we can see as these get skinnier that more and more and more of the region fills up. And so there's fewer gaps, not fewer gaps, but the gaps are smaller. And these gaps here get smaller. And these flaps here get smaller. And so we get a much more accurate approximation as that happens. So we're increasing this number of subintervals. So again, a subinterval is basically one rectangle. So we're increasing that. In other words, we're drawing more and more of them. And so the area of approximation gets really close to the actual area under the function. And so on your calculator, we're going to load on a program. It's called Riemann. Riemann is the mathematician that developed this summation method, or a method of approximation. So a lot of times we call these Riemann sums. And so we're going to put that on your calculator, and that's useful in the sense that if you have a function, if you know what the function is and you can put that into your calculator, then it'll calculate the approximation for you automatically. So for instance, we could plug in the 1/8 t squared plus 1 and find those approximations on your calculator. If you don't know the function, you have to go back and do this by hand by calculating rectangles. But we're going to put that on after section 5.5. We want you to practice by hand because that's typically the way they ask you these type of questions on the AP test. Okay, so we have another rectangular approximation, and it's a combination of LRAMs, MRAMs, and RRAMs. So remember, this is left rectangular approximation, mid rectangular approximation, and right rectangular approximation. So we call this inscribed. So inscribed is where we just stay inside the function. So if we notice this is a left, this is a left. I'm not quite sure if this is a left or a right. This looks like a left, but this all of a sudden becomes a right because the function is now decreasing. So we call that inscribed because all of the rectangles, all of the approximating subintervals, to get really mathy, are inside, or when it's inside, we call that inscribed, or below the curve. And so we refer to this as a lower sum because the word lower gives us an indication that we're underestimating the actual region. And then if we go on the outside, so if we decide to do this method of approximation, then notice this is a right rectangle. This would be a right. This looks almost like a middle rectangular approximation, and then this is a left approximation. We call this an upper sum. Again, the word upper indicates that you are over approximating the value of the region, and so all of the rectangles are above the curve, and that term is called circumscribed. So typically we refer to these as uppers and lower sums. So I mentioned this a little earlier. Rectangular approximation they're often called Riemann sums. Okay, Riemann is a mathematician, and we'll talk more about that in section 2. And so these are the ways that in free response questions they can ask you about Riemann or rectangular approximations. A tabular method, which is just what we got done doing, where they give you a table of values. We made the table, and they asked you to do the approximation. And we're going to do an anchor chart of that in just a moment, and then a volume approximation. And we'll talk that a little bit, we'll talk a little more about that tomorrow, or on day 2 of section 5.1. So here's what I'm talking about, making an approximation when when you don't have a function. So in the earlier examples, we had the velocity equaling 1/8 t squared plus 1. Now, all I'm doing is, this is still your velocity or your speed, but I'm giving you a different scenario here. So this is going to be your anchor chart that you're going to work on. So this scenario is this. You're driving down Summit at 31 feet per second, and you need to slow down to turn onto Grandview. So in this table down here are your speedometer readings over a 4-second interval as you're braking. So you started out at 31 feet per second, and then you slowed down to make that turn. So half a second later, you're going 26, then 22, then 18, then 5, 12, 10, 8. And finally, after 4 seconds, when you make that turn, you're going 7 feet per second. So on your anchor chart, I'm gonna tell you whether to do an LRAM, MRAM, or RRAM. And actually on the card, I don't think it's 4 sub-intervals. It might be a different number for the different approximation methods. But I want you to use the indicated approximation method on your card, and approximate the distance traveled in this 4 seconds. So let's develop a strategy here. We need to get this data and put it on a graph so we can start drawing rectangles. Okay, and so there is the data, and then you need to draw your rectangles. So here's an example of an LRAM. Notice we're using 8 sub-intervals here. That's why I say I don't think it's 4. I think you need to use the number indicated. So if we use an LRAM, we can do 8 sub-intervals pretty easily because we have the data for that. If we're going to do a middle point RAM, notice the difference here. If we're using an MRAM or a middle point RAM, we don't use every point. We have to increase our interval size because we don't know what's happening between 0 and 0.5. So we couldn't take the middle of that and do 8 rectangles. We are going to have to take 0 and 1, make a big rectangle out of that, and use the 0.5 as the middle point for the height of the rectangle. So an MRAM would require fewer rectangles for approximation, fewer sub-intervals. And then, but the RRAM, since we do have information every half second, in RRAM we could do 8 sub-intervals here. Okay, so so there's our strategies for our different methods of approximation. And so our rectangular approximations, also a Riemann sum. Our strategy is to identify the region and shade it in. And so, you know, for instance, we want to get that region shaded in, mark the intervals along the x-axis, sketch the rectangles with their appropriate corners or middles on the function, and then calculate the area of all those rectangles and add them up. And then make sure to put your units on. Units become really important for these applications. So now I'm going to have you, if you are in class, you'll be doing an anchor chart. If you're watching this video, obviously you're out of class and won't be participating in the anchor chart. But notice, like, this is an example of one of the cards. This group will have to do an RRAM with 8 sub-intervals. When you're done with the anchor chart, then you can go ahead and start the homework for day 1. So if you're watching this video, you can go ahead and start that homework now.